instead of saying, okay, this scientist says that this thing, and I find this thing hard to believe, right? He said this crazy thing about radioactivity that I don't understand. Instead of saying, therefore, he's wrong, say, well, what does the scientist know that I don't? Like, why does he think this? Why is he convinced? And then go find out if you can. But if you can't, if you refuse to, what's more likely? That you, the layman, don't understand because it's nonsense, or you don't understand just because it's not your field and you just don't get it. What's up, skeptics? Welcome to another episode of Reason to Doubt, your source for all things skeptical. I'm your host, Jared. I'm not Jared. I'm Jordan. I know my name. And with me is my co-host, Jared. How's it going, Jared?
It's good. It's going well. I know my name as well. So that's a good start.
Yeah. One thing that you can know with close to absolute certainty.
Yeah. Well, I'm excited that we both know our names today. We also know what we're talking about today, and we're going to talk about young Earth creationism some more and actually do a deeper dive today, specifically talking about radiometric dating, which will be fun to get into. But before that, we want to talk about our fallacy of the day.
That fallacy is the slippery slope.
Yep. So the slippery slope fallacy is basically asserting that something relatively small can lead to something, accumulate to something over time to something more significant. And it usually has a negative connotation. A good example of this would be the give a mouse a cookie book. You know, if you give a mouse a cookie, he wants a glass of milk, and then it keeps going on and on and on.
And eventually he's taken the entire kitchen. I don't remember the ending.
Exactly. But that's the idea of the slippery slope. And now that's a silly example. But also, like, people actually make this argument. So, like, some people will say, like, if you legalize prostitution, it would cause marriages to break up, which would cause a breakdown of the nuclear family and result in the end of civilization as we know it. Like,
therefore, we can't legalize prostitution.
Right.
You hear it in the gay marriage debate too. Well, if you allow gay people to marry, the next thing you know, people will be marrying kids and animals, and then
and then that's the end of the world.
So basically, it is true that sometimes, smaller effects can add up to a larger effect. And if it's a valid thing, that may not necessarily be fallacious. But where the fallacy comes in is saying that because you've moved one step towards a thing, that you will therefore necessarily move all of these other steps.
Right.
That's fallacious.
Yep.
I mean, it's entirely possible to legalize gay marriage, or as we call it now, marriage, and not say that therefore, people can marry kids. Yeah. Those two things, it doesn't follow.
They're not synonymous.
Stay off your slippery slopes. Keep your slopes nice and firm, well seated. So today we are going to be continuing off of last episode. In case you missed it, we were talking about young Earth creationism, and you should go listen to that episode if you didn't hear it, but I'll give you a real rapid overview. Basically, young Earth creationism is the position, typically a Christian position, that the Earth was created exactly as it says in Genesis chapter 1, literally taken, like word for word, exactly what it says is what happened in real life. The creation was over 6 days, God created Adam and Eve, et cetera, and all of this happened 6,000 years ago, hence the young part of young Earth.
Yeah. And so I highly recommend, if you haven't listened to that episode, go back, like maybe pause this one, go listen to that one and come back, because you'll have a little better grasp of what we're talking about in this episode.
Armed with that knowledge, now that you've listened to the other episode, because you're a good skeptic, we're going to dive into the basic claim in young Earth creationism, the fact that the Earth is young. Because if we can show that the Earth is not young, then the entire model falls apart. Makes
sense to me.
Doesn't mean that God doesn't exist or anything crazy like that, but it means that the young Earth creationism would be false.
Right. So we just take the Y off, and then we could tackle the Earth creationism part later.
Right. We could, then you'd still be left with old Earth creationism and theistic evolution, all other kinds of stuff that we also don't agree on, but that's not the subject today. So if we're going to say that the Earth is old, how can we say that? How can we know how old the Earth is?
You can't know because you weren't there.
Right. I was not there. Therefore, I didn't witness it. Therefore, it's arbitrary.
Yeah.
That's a common refrain we hear from young Earth creationists. You weren't there. How do you know? And it's important to remember that even though we physically weren't there, there was still stuff there. The rocks were still there.
Yeah, the rocks know.
Yeah, the rocks were there is actually a book published by some other skeptics I know. And it's kind of like when a detective, let me put on my J. Werner Wallace hat, like a detective coming onto a murder scene. He sees a body, there's blood everywhere, there's, a knife covered in fingerprints or something. The detective wasn't there when the dude got killed. But he can look at the fingerprints, he can take the blood samples, he can do whatever other fancy detective stuff they do, and figure out with a good degree of certainty who the killer was. That's the idea.
Yeah. So some of those fingerprints you've already mentioned one are rocks, but what are some of the other fingerprints that we can look at when we're trying to date the Earth?
So there's a lot of different ways that the Earth's age can be known to certain degrees. The entire field of geology is based around this. So we have like how long it would take rocks to form, and then we, can see how many layers there are, and that tells us it doesn't necessarily give us a great clock for the entire age of the Earth within a very precise range, but it can certainly tell us that the Earth is way more than 6,000 years old because we can see rocks that take more than 6,000 years to accumulate, right?
And if we're just trying to debunk that the Earth is young, that's enough right there.
Right. Like if there's a rock layer and that rock layer would take 1 million years to form, young Earth creationism is dead in the water, just right there. But other things, we could look at cosmology. We can look at stars and their life cycle and observing that we have stars from successive generations, and that would show that the universe at least appears to have however long how many billions of years it would take for that to happen. The prevalence
talked about light last episode too, so we know that light travels at a constant speed
thanks to Einstein's theory of relativity. And so, that's another way. So these are all great ways we can know that the Earth is not 6,000 years old. And importantly, all of these answers agree with each other, and they didn't have to. Nobody forced these answers to coincide. If physics were different, if the world were different, if the Earth was in fact 6,000 years old, there's no reason why all of these different fields would have yielded the same answer.
Right. Well, so if we're looking at rocks in geology, you could tell me that it takes, 1 million years for a rock to form or something. But if I just look at the rock, how do I know how old it is? How would you date that rock?
So that's a great question. So many years ago, back when Darwin was still doing his work, before they discovered radioactivity, you might have tried to use index fossils or things like that, but you would have been kind of out of luck in order to get a really good date. But now that we understand how radioactivity works, we can use what's called radiometric dating. Radio for the radioactive decay, and metric because it's a measurement.
Is it the imperial system or the metric system?
Definitely metric. There's no imperial radiation units. I guess actually there are. There's REMs and RADs, but we don't use
imperial dating.
We don't use those. We use becquerels and sieverts like normal civilized people. Radiometric dating is a way we can date rocks and sometimes other things, but it's usually rocks or crystals. And it allows us to determine how long it has been since that rock or thing was formed, or in the case of radiocarbon dating, since the biological thing died. Usually, though, I'm going to kind of put radiocarbon dating to the side because you wouldn't use that to figure out how old the Earth is. For reasons that I'll go into. So I'm mainly going to be focusing on other radiometric dating methods.
I will say, though, the radiometric carbon dating, it seems like that is a usual go-to point for young Earth creationists because they can say that it's not an accurate dating for dating the age of the Earth, which it's not, right?
It's not. I mean, it certainly is enough to refute young Earth creationism, so I don't know why they point to it anyway. But
yeah.
So here's how radiometric dating works. Well, hold on. Before I get into that, here's how radiation works. And in case anybody is new to this podcast, I'm a nuclear engineer. I'm not a nuclear physicist, but I do know a little bit about radiation. I'm also not a radiogeologist, but in terms of like the theory, I have a basic grasp of what's going on. Hopefully, I say that now. Hopefully, I don't mess up. So, there are elements that are unstable. Usually, it's because they have a disproportionate amount of neutrons and protons in their nucleus. But for whatever reason, they are unstable, which means over time they will decay. They will go through some sort of process, and that will push them into another state that'll make them closer to stability. So usually what happens is it emits some kind of particle. It might eject a neutron, for example. One of the neutrons might become a proton, in which case it would have to eject an electron in order to preserve charge because it went up. I think I'd have to write it down to be sure. But anyway, it'll preserve charge and everything. But usually it'll go through some process, eject some stuff, and then turn into either a different isotope or a different element. So some verbiage before we go much further. Elements are determined by how many protons they have. So if something is one proton, it's hydrogen by definition. If something has two protons, it is helium. Always. Isotopes are the same element, but with a different number of neutrons. So hydrogen by itself, just a proton, that's just hydrogen. If you have hydrogen and a neutron, it's still hydrogen, but it's called deuterium. That is a different isotope of hydrogen. Two neutrons would be tritium, and so on. So if I say isotope, it's the same element, just different amounts of extra stuff. So after radioactive decay, the thing in question will become a new isotope, perhaps a new element as well. And that will keep going and going until eventually, however much in the future, the stuff is stable. It reaches an element or an isotope that doesn't decay anymore. It'll just sit there forever. Often that element is lead, but not necessarily. So there's your crash course in radiation. If you want to know why things that are unstable decay, that's like deeper physics, and you're going to have to hit the I believe button for this podcast. They do. So how can we use that? Well, one interesting thing about the way radiation works is it happens at a very predictable rate. That rate is described by a number called the half-life. You've probably heard that term before. The half-life is the amount of time it takes for a amount of stuff to decay, so half of it remains. So if I had a kilogram of uranium, say, in one half-life, I'd have half a kilogram. And in another half-life, I'd have 1/4 of a kilogram, because it's the half halved again. Right. Yeah. And so on, half, all the way down. So it's an exponential curve that flattens out. But basically, with this half-life, we can say how long any sample will take to decay to a certain activity level. So we can basically do math to look into the future and see how long it'll be radioactive. We can also do the same math to go backwards into the past and see where it came from, because it's predictable in both directions. With this, we can do something interesting. We can look at radioactive material in the Earth, see how long it's been decaying, and then that tells us how long it's been around.
And I guess my only question here is, how would you know how much of the material there was to begin with?
So that's a common YAC objection. So let me explain a little bit more about radiometric dating. So when you have something decay, the thing that did the decaying, we call that the parent. And the thing that's left over afterwards, that's the daughter, because the parent gave birth to the daughter isotope. If I have some parent, it'll decay and it'll lead some daughter, and that'll happen at a predictable rate, right? So if hypothetically we knew how much parent and daughter there was at the beginning, then went away, did some stuff, whatever, came back, looked at how much parent and daughter there is now, we could use those 2 points of information to tell us how long it's been. And that's the basic theory that radiometric dating is based on. It requires that we be able to either make some kind of statement about the initial conditions of the thing, of the crystal or whatever we're examining, or be able to manipulate the formula such that that's not important. It requires that the half-life has been constant throughout time, and it requires that the sample has remained undisturbed. So like you haven't had extra radioactive material thrown in, because that would give you an erroneously old date. Or on the other hand, had radioactive material pulled out, because that would make it look younger than it actually is.
Right.
That's radiometric dating in a nutshell. There's a bunch of different methods. There's tons of different methods. You've got radiocarbon is one of them. You've got uranium lead, which is a really good one. Argon, lead, rubidium, strontium, tons of different methods. Each one is a little bit unique. Some have extra assumptions based on like the characteristics of the isotopes involved. All of them have more or less the assumptions I just listed. Some other ones might have other idiosyncrasies, which, but they all kind of paint the same picture. This is sort of a similar situation what I was saying before. All of these radiometric clocks are independent. They're using different elements on different samples. There's no reason they should agree randomly. The fact that they typically do agree tells us something. So your question was, how do we know what the parent-daughter ratio, how do we know how much stuff was there to begin with, right? Because we weren't there.
Right.
Yeah. That's the first of three objections that I'm going to answer from the EC. That it was undisturbed and that the half-life hasn't been changed. So initial ratios. How do we know that it was like that in the beginning? Well, that depends on the method. So one way is if we're dealing with something that used to be magma, which often it was. Often when we're doing a dating method, we're dating some kind of rock that's formed by cooling magma or lava. And crystals will form in that cooling structure, trap radioactive material inside. And then because it's like stuck in a crystal, it'll just keep decaying away and stay inside the crystal until a scientist goes and breaks it out. And then what we're measuring is how long it's been since it melted. So the last time it melted, that's what we're measuring.
Because when it was trapped in that crystal, you could say, okay, this is what it would have been like had we trapped it in the crystal yesterday.
Well, it's locked in the crystal, so now like nothing can get in or out.
Well, I'm saying is like what was locked in the crystal would have been known, right? Because that gas couldn't have been older than when it got locked in there.
Well, so if it's a gas that you're measuring, so in the case of argon dating, so in the case of potassium argon dating or argon dating, the argon, the daughter element, is a gas. So it's not going to stay in the magma. It's going to like bubble out, right?
Okay, I got you.
And so the idea is when the crystal was formed, there was no or very little argon there already. So it's called outgassing is the process. And so the idea is this gas would have escaped, the crystal would lock in with little or no gas in it already. So any argon we find in there came from the decay. Now, I'm going to tell you right now that assumption is usually not followed exactly. Typically, there's some amount of trapped argon, and that's called inherited argon. So, oh my God, I guess we just have to throw away the whole method, right? No. So we can actually detect through other methods how much stuff was trapped in there. This goes for not just argon, but other methods too. So often there is another isotope of the daughter. So in the case of potassium argon dating, potassium 40 decays into argon 40. But there are other isotopes of argon that are not from radioactive decay. So they are stable. They don't come from radioactive stuff. They would have just been there. Okay. And because isotopes are chemically identical, doesn't matter what isotope of argon you have, any chemical process will treat them exactly the same. If it trapped the radioactive argon, the stuff that comes, the radiogenic argon, the stuff that comes from radioactive decay, it would also trap the non-radiogenic argon. And so if we detect non-radiogenic argon or any non-radiogenic stuff, we know that there was stuff in there to begin with. Does that make sense?
Yeah.
Another advantage here is it also gives us a sense for how much was trapped. And it's usually somewhere on the order of like 50 to 200,000 years or so worth of argon. So if, say, we grabbed a crystal, it was freshly trapped, it grabbed some argon, we tested it, it would show up as 200,000 years old, even though it was just yesterday. And that sounds awful, right? That's not very accurate. Well, that's why you have to use the right method for the right situation. So if you have a sample that's 1 day old and you have a 200,000 year error, that's a big deal. If that same sample is 1 billion years old, 200,000 years doesn't matter anymore, right?
So each one of these dating methods has particular uses and will like fine tune based on how old the sample is you're testing.
Yeah. So generally speaking, the longer lived the radioisotope is, the older things you can date with it, just because it'll take longer to decay, so there'll be more of it around. But by the same token, it takes longer to decay, and so if you try to use it on samples that are too young, any signal will get lost in the noise. You won't have enough decay have happened to really measure it. Right. So it's kind of like imagine, and creationists will look at that like, oh, they love going to Mount St. Helens, for example, which we know exactly when that erupted, right? And so they'll pull a rock or a crystal from Mount St. Helens, do uranium, lead, or potassium argon dating, which you do on samples of millions and billions of years old, and say, oh my God, there's a huge error. Look, radiometric dating isn't accurate. And that's like you went to like those truck weigh stations you have on the side of the highway, right? Threw like a handful of salt on it. It's like, oh, it didn't register. Psh, this scale's useless, you know?
Yeah.
Yeah. So yeah, that's ridiculous. Now, so that's argon dating, right? So often we can tell by the presence of a non-radiogenic isotope. Sometimes we can tell by just like the physics of the situation how much would go away. And if one of those assumptions is violated, we can usually tell by the dates we get. We'll actually track a bunch of samples. So they don't just like get one crystal, date it, and say, okay, that's good. They'll like do a bunch of samples in the same area. So like this lava flow crystallized, they'll grab a bunch of crystals from different parts of the flow, and they would have trapped different amounts of gas, but they would have been decaying for the same amount of time. Right.
So you would have been able to compare each one to the other. So.
Right. So you might get some error from one or two, but if you have 15, 20, 30, you know, that kind of starts to even out.
Right.
So that's the less cool way you can do it. But there's a much cooler way you can do it called the isochron method. And for the isochron to work, we're going to turn to the gold standard of radiometric dating, which is uranium lead. It's one of the best radiometric dating methods there are because it comes in with a built-in double check. So the way that uranium lead works is you'll have a zircon crystal. Zircon will trap uranium easily, but it will not easily trap lead. Okay? It will trap some, but not much. The uranium decays through a whole chain, like it goes through a bunch of steps, but eventually it decays into lead. So there are two different kinds of uranium, uranium-238, uranium-235, and they decay into two different kinds of lead. Uranium-235 goes to lead-207, uranium-238 goes to lead-206. You don't need to know any of those numbers. The important thing is that there are two kinds of uranium, and they decay into two different kinds of lead, and they decay at different rates. That's what's important. And so we get two clocks for the price of one. We get a clock for uranium-235, and we get a clock for uranium-238. And if nothing's happened, and everything's, you know, all our assumptions are working, those two clocks should agree with each other. So that's one nice thing about uranium lead dating. Another nice thing is because we have two different kinds of lead, but there's also non-radiogenic lead that doesn't come from uranium, we can do something cool called isochron dating. And basically what you do is you mathematically manipulate the formula. So you put everything in terms of ratios between what you can measure today and the amount of the non-radiogenic isotope, which you can also measure today and hasn't changed the whole time. That's very important. So because this non-radiogenic lead, which remember, doesn't decay from anything, it's just hanging out. That amount of lead will stay the same the whole time. You can use that to eliminate mathematically the original amount of parent and daughter. You don't even need to know it. You actually figure it out from the measurements you get today. You can actually determine how much was there at closure based on what you measure today.
That sounds really cool, actually.
There's some math involved, which I'm not going to try to do over a podcast. If you're interested, I will try to remember to, I did a proof of the isochron formula. I'll try to post that proof if anyone wants to check my math, or you can just Google the isochron formula. Otherwise, look it up later and or take my word for it, but it does. It works. So that's objection one. The initial parent and daughter ratios we don't need to know, either because it's taken care of by just physics, or we can work around it, basically.
So the other one that they bring up is like, well, how do you know that something didn't disturb your sample, right? Like, how do you know somebody didn't put something in there, or somebody didn't take something out along the way? Or like,
yeah. And this is a valid concern, which is something that researchers are actually, concerned about, because as the radioactive stuff is decaying, it's going to damage the crystal. And if it damages it enough, it can make it so that stuff actually does get in and drain away things. So It is a real thing that happens. Ways that we get around this, first of all, if it's been disturbed, particularly in something like uranium lead where there's two different clocks, because anything that takes away one type of uranium will take away the other one, and lead the same way. But because they decay at different rates, it'll make the two dates not match.
Gosh, so and that's what's cool about uranium lead is you can check it against itself. Like if the dates are off, you're like, something's off here.
Right. You can actually do some fancy math to still get a usable date, even in that case. It's called discordia, but we don't need to go into that. The point is you can detect if something went wrong, basically, is one way. Another thing to keep in mind is most often, it's not like some fairy is smuggling in uranium, typically. Usually what's happening is water or something is leaching stuff away, right? And so if this process were leaching away, say, the uranium, what it would do is freeze the clock. It would stop decaying, right?
I got you.
So that any test you did would tell you how much, how old it was, like a minimum age, but you wouldn't be able to tell its actual age.
You could tell the age when it got started leaching, basically.
Yeah. It would freeze time at that point. So you know, okay, well, it's at least 50 million years old, but we can't say how much older than 50 million years it is. But it's not younger. We can tell that.
It's not 6,000 years?
Not 6,000 years, right. Or it could leach away the daughter element. So suck away some of the lead. And that would actually make it look artificially young. So if you've got a sample that's 1 billion years old and you take away half the lead, like 500 million years worth of lead, the test will say 500 million years, even though it's actually 1 billion. So this actually works against the creationists. Like if that happened, all it would mean is the rock is even older than we thought.
Right. So you're using their own objection against them, basically, at that point.
Basically, yeah. Like there are ways we can detect it. There are ways we can address it. But even if we just take it at face value, it still doesn't help their case. So I have to use the bathroom. I'll be right back.
Yeah. So basically with this undisturbed objection, we have ways to either detect that a sample was disturbed, and we also have ways to mitigate that, and in some cases still figure out an age or a relative age based on these processes.
Right. Of the three, I'd say this is the most valid objection. It's something that is known and is taken care of and addressed, but it is a real thing that researchers or scientists do have to actually take into account. So this is an actual phenomena that is very important to the field of dating, but it's something that it's not like scientists are just, winging it out there,
I guess the big thing with this is if a sample was disturbed, you would know it by the testing, right?
Yeah. You'd be able to detect if the sample was disturbed. And another thing to keep in mind here is okay, real talk. Let's say that some samples were disturbed, right? And maybe we missed it. Let's just say that happened. Well, we still have thousands of samples, tens of thousands of samples that are dated all across the world by different researchers of different persuasions over and over and over again. Every day, these tests are being run. And consistently, all the time, they come up with old ages.
So it's not like you test one sample. Oh, this one's young. I guess we'll just throw out these other hundreds, thousands we tested.
We just have a mountain of data of all of these tests, and any kind of disturbance wouldn't have disturbed everything the same way, right? So, yeah, that it doesn't undermine the point.
Gotcha. Well, I guess, what about the half-life, right? Like, isn't it possible that the half-life could change or it could be constant over time? Like, how do we know that?
Is it possible that it can change? No.
Oh, okay.
Anyway, so the half-life is determined by like constants of physics, like the strength of the strong and weak nuclear force and things like that. So very complicated stuff. It would require that those physical laws would change in order for the half-life to change. So in order for the half-life of most things to change, let me put an asterisk there. So on its face, it seems unlikely, but hey, maybe the laws of physics have changed over time or something, First of all, the nuclear processes are occurring in the nucleus, the middle part, the tiny part in the middle of the atom. Okay. Most processes that happen are chemical and they are mediated by the electrons. Okay. So the nucleus is very well insulated usually from the environment. Like the nucleus, the protons and neutrons, they don't have any idea where they are, what they're doing. They don't care at all. The electrons handle all that. So like just these numbers are not exact, but just to give you like a feel for the relative size of things. If a nucleus was like a nickel in the middle of a football stadium, the nearest electron would be like outside the stadium or outside the parking lot. And that's like the closest electron. And for like uranium, there's like 90,
So you're taking the metro into the...
Right. They're just very far away. So we've measured half-lives under extreme heat, under extreme pressure, under extreme cold, in vacuums, out of vacuums, like all different kinds of scenarios. And the half-lives don't change. Our measurements get better over time. And like, if you like look at a different source, you might get a slightly different half-life because like there's measurement error, we're not perfect when we're measuring these things. So like one place might say it's 1.9561 billion. One place might say it's 9.562 billion or,
right.
Whatever, but very close. Now I said most, and I've been very careful about that because if you hear like in debunking circles, they'll usually just say half-lives can't change. Never been observed to happen ever. And that is not strictly true because there are certain kinds of interactions, certain kinds of decay, specifically electron capture is a prominent one, but beta decays in general, of which electron capture is sometimes classified as beta decay, sometimes not. Nobody but me cares about that. The important thing is, so let me just talk about electron capture. So the way that most radioactive decay happens is something happens to the nucleus and it's just like, oh, I'm going to decay, and it doesn't. Okay. And it all happens in the nucleus usually. For a few types of decay chains like electron capture, the electrons are involved in the process. The way electron capture works is you can imagine the electron as a particle orbiting the nucleus. That's not what it is at all, but just to visualize. And the electron kind of falls into the nucleus. One of the protons, because charge has to be conserved, so you have a positive charge, they absorb the electron, that cancels that positive charge, it becomes a neutron. Boom, now it's something different. Okay. And so that's actually relevant to potassium-40 and argon-40 decay, because you notice the 40 didn't change. That's the number of nucleons.
But the name in front did.
But the name in front did because the number of protons changed. So, anyways, that specific interaction has been shown to be somewhat vulnerable to environmental conditions. First of all, if you just went extreme and stripped the atom of all of its electrons, like totally ionized it, and so like it's just a nucleus, well, it can't decay by electron capture because there's no electrons to capture anymore, right?
Right, yeah.
So that's like at the extreme end. But there's also been experiments where like under very extreme pressures, and we're talking the kind of pressures you get like tens of kilometers down or further, you might get a change in a couple of % of the half-life. Like significant, it's an important finding, but it doesn't like it's not enough to change your dates from, 2 billion years to 6,000 years. Like, it's just not enough. And I cannot emphasize this enough, that is only for very specific types of radioactive decay that involve the electrons. Most are not like that, and would not, like, the electrons are not involved at all. And
you have other things to compare them to that don't have that kind of change.
Right. So if you hear a young Earth creationist tell you that they determined that half-lives could change by whatever percent they give you, usually it's like, 6,000% or some crazy number. If they tell you that, then you should obviously ask for a citation. And I would be very confident that what they're talking about, first of all, they're probably going to get the number wrong and have the citation wrong and everything else. But what they're probably talking about is some kind of beta decay, probably electron capture. And so they're going to naively say, this type of radioactive decay changed, therefore they all can change, because they don't understand how it actually works. I don't expect most people to know this stuff. Like, before I studied nuclear engineering, I knew that radioactivity was a thing that existed. I didn't really, I was a young Earth creationist too, but I didn't really understand anything about it, because why would I? It didn't have anything to do with my life, So I don't expect people to be experts on this. But if you're going to try to overturn an entire field of science, you should probably brush up on it a little bit, right? So that's so the half-life is unlikely to change, but let's just say it did. Okay, however it happened, maybe God changed it or whatever. Okay, let's just say it did. That has some consequences. And those consequences aren't great. In fact, they're pretty terrible. Because if you shorten so what they want to do is they want to say, okay, if we shorten the half-life enough, we can get all of the billions of years of decay we see and just cram it into, usually they want to do it at a Noah's flood, because stuff's going down and things are exploding and water's in the deep and everything else. So we'll just have the radioactive decay happen then too, right? Just cram it all into the flood. So that's going to require a significant change in the half-life, a lot, okay? Well, so when something decays, I told you before, it releases a particle. Those particles, or often it does, and heat. And those particles have energy. So it shoots, let's say it shoots off a neutron or something. That neutron has energy and it bounces around in stuff that's going to heat it up. That's how temperature works, right? So when, in addition to the radiation it's also releasing energy. And that happens every time it decays. Okay. So if you have 2 billion years worth of decay, you've got so many decays, so many numbers of decays that had to have happened. Whether those happened in 2 billion years or whether they happened in a day or 6,000 years, or pick your number.
It doesn't change the amount of decay that happened, right?
Exactly. The amount of decay is the same regardless of how fast it happened. Okay. And so if you want it to speed up, if you increase the half-life or decrease the half-life, if you make it decay faster, if you make it shorter, if you decrease the half-life, you increase the radioactivity. By definition, they are two ways of talking about the same thing.
When you move one, the other one moves.
Right. They are related to each other mathematically. If you change one, you change the other. You just do. By definition, you do. Okay. So if you want to cram 2 billion years worth of decay, you also get 2 billion years worth of radiation and 2 billion years worth of heat, all released in 1 year. Now, how much could that really be, right? I mean, you can hold uranium in your hand, natural uranium. You can just hold it in your hand and you'll be fine. I wouldn't recommend rubbing it on your skin and keeping it there for years or anything. But I'd be perfectly happy holding a chunk of uranium in my hand. It's not going to hurt you. Not over the brief period of exposure, no big deal, right? And it's not going to feel warm or anything. It's not like this is The Simpsons where you've got the glowing stick. Caveat: do not touch a fuel rod after it goes into the reactor. Before it goes in, you can hold the pellets in your hand. That's fine. Do not touch a fuel pellet after it goes into the reactor, because you'll die. But yeah. Anyway, It turns out, though, if you try to cram 2 billion years or 4 billion years, how many billions of years, you release a lot of heat. And so...
How much heat?
Well, Jared, I'm glad you asked, because I did the math. I'm going to post this link, too, to a Google Doc where I kind of break down my calculations. I decided that I would calculate how much heat would be released. So here's what I did. I figured out how much heat is released every time uranium. So uranium, I did uranium 235, 238, thorium 232, and potassium 40, because those are the 4 biggest contributors to the heat in the Earth right now. We know this because we can actually measure its decay right now. So a group did a really interesting study of geological neutrinos. Neutrinos are released when radioactive decay happens, some of them, specifically the ones that are involved with uranium and thorium. Neutrinos are really cool particles that don't care about matter. They almost never interact with it. Like neutrinos, you're like being bombarded with neutrinos all the time. They can go through the entire Earth and never touch anything. Okay?
That's crazy.
Yeah. So like to detect them, you have to have like these huge, massive pools of water. And every once in a while, a neutrino of the millions that are flowing through it might hit a like water molecule and you can detect it. So it's really hard to detect. But they did it. And so they used this to infer, to calculate how much decay was happening and like what it was coming from. And so they got like an empirical number of the heat that we're getting from the Earth. From decay right now. The group that did it is called Camland, Kamland, and they calculated 20 terawatts of energy coming currently, like today, 20 terawatts of energy. So that's how much heat we're getting from radiation in the Earth's crust, but mostly the crust, some in the mantle. So I did the calculations to go through the entire decay chain from uranium, thorium, the whole way down, the energy from every step along the way, added it all up. I looked up how much uranium was in the Earth today, how much thorium is in the Earth today, etc. And then I took 2 billion years, and the reason I did that was the Oklo phenomena, which I'll talk about why, because that's just the coolest thing ever. I'll talk about that in a minute, but just I took 2 billion years of the amount of decay, right? And then I did a bunch of math that would tell me how much energy that was, which you can go look at the Google Doc if you want to see all that math. It took a while. But the amount of energy released after all of that stuff from the decay of the uranium, the thorium, if you sped up all of that decay and everything, if you do all that, I calculated it for just the crust. I ignored the stuff deeper in the Earth because the stuff on the crust is what really matters. So it was 0.5 times 10 to the 30th joules. Probably have no idea how much energy that is, right? So let me try to encapsulate how much energy that is in terms that you're kind of used to. If you assume the entire Earth's crust is made of granite, which a lot of it is, a lot of it's not, but it doesn't really matter. Pick a rock. It doesn't even matter what kind of rock it is at this point. You'll see why in a second. Take that rock, right, and throw all this energy at it and see what happens. The temperature of the rock would be if it was all granite, after it took all this heat, would be approximately 27,000 degrees Celsius.
That's a lot of Celsius.
That's enough to vaporize the rock. It would not be rock anymore. Now, granted, that's like without heat rejection. So this is like, if you assume it didn't reject any heat, where would the temperature be? But it can't reject heat fast enough to stop this cooling, right? We're talking like energy levels that approximate, it's like a significant portion of the sun's total output. To put it in terms that everyone's familiar with, everyone knows the sun. Sun's really hot, right? And it releases a lot of energy.
It also helps with the
entropy, the second law of thermodynamics. It also helps with
entropy, yeah.
It does, yeah. Earth is not a closed system. Newsflash, we've got the sun. So the amount of heat that would be released by this decay would equal about 22 minutes of the sun's total energy output. Now, granted, it's spread over a year, but this is the whole sun. 22 minutes of it. That is a literally astronomical amount of energy. This would be an amount of heat that would vaporize the crust, blast away the oceans, boil them away. Like, Noah is so dead, it's not even funny. I ran other calculations just for fun, and the amount of potassium in your blood, you have potassium 40 in your blood right now, right? Because you live in a radioactive environment. You have potassium in your blood. Some small portion of it is radioactive. The amount is very, very small. It's not a big deal. It's not a big deal until you speed up the half-life by about 2 billion times. Then it's actually enough heat to boil your blood.
Yeah, so the idea here is that if you want to speed up the half-life to make it fit with your 6,000 or 5,000-year-old Earth at that point, it has major ramifications.
Oh, but wait, I'm not done, because it's not just the heat, right? Heat is a problem, but you know what else gets sped up? The radiation, the radioactivity part, right? So, like I said, we live in a radioactive environment. That means that the stuff you eat is also radioactive to a certain extent. The bread that Noah would have eaten would have been so radioactive, it would have killed him in a matter of hours. Like, his bread would be a dangerously radioactive environment. Like, this is how ridiculous things get when you increase it by billions of times. Like, the Earth would be a radioactive wasteland with nothing left. It would be just like the entire crust would be gone. Like we're talking like melting the Earth levels of heat. And we know that this never happened. I mean, obviously we know this never happened because like the oceans are still here, right?
Yeah.
But other things, there's other ways we know it never happened. In granites have uranium in them often, a lot, like more than other rocks.
Mm-hmm.
And you can see discolorations in the uranium from the damage, discolorations in the granite from the damage of the decay. As it damages the rock crystals, you get like discolorations in a ring around the uranium. They're called uranium halos. And they also have fission tracks. So like very occasionally, uranium will fission spontaneously. And it's like a very energetic reaction. You can see like a little track in the rock where the highly energetic particle like barreled its way through the rock, basically. Well, these damages go away if you heat up the rock. If you heat up a material without melting it, it can remove these damages. It's called the annealing is the process. We use it whenever we if you stress metal, if you bend it a bunch, it hardens it, right? Well, if you heat it up gently, but don't melt it, it'll return to being pliable. You've annealed it, right?
When people make knives and stuff, they'll heat it back up, after the hardening process to give it some softness.
Exactly. That's precisely the same thing. Well, these tracks are wiped away if you heat it up, and you don't have to heat it up very much. I think it's like 100 degrees Celsius is enough to wipe away these tracks. So the fact that we still see these show that the rock has never been heated up more than 100 degrees, right? Not 20,000 degrees for sure, right? Yeah. And here's the hilarious thing. So this is not new information to sophisticated young Earth creationists. If you go to the RATE project, so these are the people that I believe it was ICR sponsored, people with actual science degrees. They got together and they tried to figure out how accelerated decay would work. Okay. And so they looked at the halos, they looked at fission tracks, and they figured out okay, if we know the Earth is 6,000 years old, so we think that maybe it sped up and made these halos and all that stuff, right? Well, they identified in their papers the heat problem, and their numbers, which I did my own calculations, but they came up with very similar numbers. And you know what their answer was?
Let me guess. The water cooled it down?
No, that's something that the bottom of the barrel young Earth creationists say, right? Okay. Because it's ridiculous. No, what they said is, we don't know. Maybe God did it. They just have no answer, which, I mean, fair enough. At least you admit that you don't know. Okay, cool. But it is a known problem that they have no solution for beyond exotic physics. Oh, side note, just something cool, just because I'm proud of it. I ran the numbers. So I did the heat numbers for everything that was decaying, right? and like back in time and all that. I did the calculations again for just like the present day, and I calculated 21.3 terawatts compared to the empirically measured 20 terawatts, which is an error of like 6%, which I am very happy with. Like for some back of the napkin math I did in Excel, I'm pretty, yeah, that's not bad, right?
Yeah.
Yeah. So empirical verification, we're doing science over here. So
well, you had mentioned something earlier about the Oklo phenomenon.
Okay. Yes, Oklo. I'm so glad you reminded me, because everyone brace yourselves. This is the coolest thing that has ever happened in the history of the universe, right? And I know we're going on a while. I don't know after editing where we're going to be, but we're getting close to an hour. But buckle in, because it's totally been worth it just for this. Okay. Jared's shaking. You guys can't see, but Jared's shaking his head in disbelief. Okay, so I've hyped this up. It's going to live up to it. In Africa, they have uranium mines. One of the mines is at Oklo, O-K-L-O. And when you're taking uranium out of the ground, they measure how much uranium-235 there is. They measure the enrichment. So the enrichment is just like the percent of the uranium that is the 235, the good stuff, basically. The rest is 238, which you can't use for water reactors or bombs, which is what they're more concerned with, right? Because if people were like taking a bunch of uranium, that would be a problem, right?
Yeah.
So uranium the world over is about the same enrichment. It's about 0.7% enriched, and it varies very slightly, but it's pretty much the same the world over, because all the uranium came from the same place when the Earth formed. Well, they determined, this was back, I think, in the 70s, they measured the enrichment, and it was like 0.6% enriched, which doesn't sound like a lot, but that's a big drop. They were missing some uranium-235, and people were like freaking out, right?
Where did all this extra uranium go?
Right, where'd the uranium go?
Yeah.
So they investigated, and they found that none of it was missing. That was just the enrichment when they pulled it out of the ground. It appeared to have been depleted, as if some of the uranium had been burned up. Okay. And as they were investigating more, they found fission products. So they found stuff that come from the decay of the things that are left over when you do fission. And fission is when uranium absorbs a neutron, it splits into two or more pieces, and that's how we use nuclear reactors. So there's a very specific spectrum of things that come from fission that don't come from in the same prevalences from other reactions. Okay. So like if you see a certain, like it's basically like a fingerprint of fission, whereas it was some other process, you wouldn't get the same stuff in the same amounts, if that makes sense.
It pretty much says like there was a reactor here.
Right. Exactly.
Or the process of a reactor. So
here's what happened. And this what's really interesting. This phenomena was actually predicted ahead of time by a Japanese researcher by the name of Paul, I believe his name is Kuroda. I'm probably mispronouncing it. But he figured that there would be naturally occurring nuclear reactors, and here's why. So the amount of uranium enrichment is 0.7% today, right? The good uranium decays faster than the fertile uranium, the U-238. So in the future, uranium will be less enriched. Okay, because the stuff that is it'll keep decaying. So the 235, the fissile material, will decay faster than the other stuff, so it'll progressively get less enriched. Well, if you go backwards, it becomes more enriched, right? For the same reason. You can just plot this on a curve, and you can look back in time and see how enriched it was in the past. Natural or nuclear reactors that use water in order for their moderator, which I'm having to restrain myself not going into all these things, require about 3% enriched uranium in order to work. If you don't have an uranium to that, it's not like it'll work a little bit. It just won't. You won't get the chain reaction that you need. Okay. So you have to have at least that much enriched uranium, and you have to have water. Well, turns out that about 2 billion years ago, natural uranium was at that enrichment, the enrichment you need in order to sustain fission. And uranium is soluble in water in the presence of oxygen. Okay, so about the same time that a bunch of oxygen was showing up in in the atmosphere, you also had uranium at the appropriate enrichment. So what he predicted would have happened is somewhere in the world, you'd have uranium that would get deposited in an area. It would be in the presence of water. That would allow fission to happen, and you'd have a naturally occurring nuclear reactor. The guy predicted it, didn't think he'd ever see it happen because, I mean, what are the odds that we just stumble on the right spot? And wouldn't you know it, like a decade or two later, they find it in Africa, a nuclear reactor totally made by nature that existed 2 billion years ago. And what probably happened is like the water rushed in. Okay, so you'd have it in water. Boom, nuclear fission happens. It boils the water, right? Because there's a bunch of heat that's just going out of control. The water gets all boiled away. When there's no water, the fission shuts down. Water rushes back in. Rinse and repeat over and over and over again. And until eventually you burned up enough uranium that you can't sustain fission anymore.
And that's why when they go to pull it out of the ground.
Right, there's less uranium than there should be. Fast forward 2 billion years. Now, this is super useful for a lot of reasons. First of all, this is something that happened for sure. Even creationists can't dispute that this happened. Like if you go to AIG or ICR, even they don't dispute that Oklo means a nuclear reactor occurred there. It's just, it's incontrovertible. The depleted uranium, the fission products, like that, there's no way around it. Fission happened here, right? This is an event that's 2 billion. It requires 2 billion years to get to happen. So that right there shows that the Earth is older than 6,000 years, right? Also, it shows that physical constants haven't changed, but so much. Because if the constants changed, then you'd get different prevalences of the daughter elements. So
Right.
it would look different, basically, but it doesn't, right? So this, like, you could maybe tinker a little bit, but it like puts bounds on how much could have possibly changed over that period of time.
So it kind of debunks the whole changing of the half-life and all that stuff.
Right. And it gives us a nice anchor. If they're going to say, okay, the half-life changed, well, it would have had to have changed enough to get 2 billion years worth of decay. Because like Oklo, we know for a fact that happened. It's something that even creationists agree happened, which is why I use 2 billion years in all of my calculations. So I'm anchoring it to something that the creationists will agree with. But there's your bonus, not radiometric dating, but radioactivity related reason that we know the Earth is old.
That's pretty good. I mean, those three things right there, I think alone, just answering those objections, prove without a shadow of a doubt that the Earth is older than 6,000 years, if not older than 2 billion years. Or
the Earth is in fact 4 billion years old, 4.5 billion years old. That's the oldest rock we found. Well, the oldest rock we found on Earth is a little bit younger than that. I think it's like 4.2 or something like that. Mm-hmm. And then asteroids and things that like ostensibly formed about the same time as the Earth did have been dated about 4.5 billion. So the oldest rock in here is like a little bit over 4. Space is 4.5. Okay, that gives us about the number. Yeah. Well, I honestly, radiometric dating. Like I remember in the debate between Can Ham and Bill Nye. Bill Nye was asked by an audience member, aside from radiometric dating, how could you prove that the Earth is old? And he was like, but radiometric dating's so good. Like, why would you?
Yeah, why would you not do it? Yeah.
Right. Like, and that's how I feel. Like, sometimes people ask me the same thing. Like, okay, well, aside from that, it's like, what do you mean aside from that? Like, that's the thing. Like, that's not like, yes, there's other ways we know, but like, come on. Like,
well, I guess, from a layman's standpoint, like, and I'm a layman in this, I can understand why people would still hold to a young Earth belief if they didn't grasp like what was going on here, right? Like there's a lot of math going on. There's a lot of things you have to understand, a lot of terms and stuff. And so like somebody telling you this without actually grasping the material, it may be hard to wrap your brain around. Right.
Right. Which, I mean, that's how I feel when my biology friends try to explain like the super deep ins and outs of how evolution works. Like I understand like basically how it works, but like when they start about like in the weeds, my eyes just kind of glass over. And, I have a really hard time following what's going on. So I don't blame people for not like at kind of like a deep level really grasping everything because it's a complicated subject. But it's a complicated subject. So you shouldn't say, well, I don't understand,
therefore
they're wrong. Like, I don't understand the science, therefore the scientists are wrong is not smart. Like, it's not the right way. Like, instead of saying, okay, this scientist says that this thing, and I find this thing hard to believe, right? He said this crazy thing about radioactivity that I don't understand. Instead of saying, therefore he's wrong, say, well, what does the scientist know that I don't? Like, why does he think this? Why is he convinced? And then go find out if you can. But if you can't, if you refuse to, what's more likely? That you, the layman, don't understand because it's nonsense, or you don't understand just because it's not your field and you just don't get it. Like,
right, exactly.
What's more likely? Let's be real. Like,
and I can guarantee you, if you really do want to know, there are people like Jordan out there who will be happy to take out 20 minutes of their day to sit down with you and explain the process. Like, I've never seen Jordan not turn anybody away when it comes to talking about this stuff. So
if somebody was like, hey, I know you're busy, but I heard about Oklo. I would literally drop everything I'm doing. Like, let me talk to you about radiation. Yeah. Like,
so there are people out there who will happily break it down Barney style for you, like, if you need it to. Like,
yeah. Well, we've been going for a while. There's more we could talk about regarding radiometric dating. It's an entire field, but I think that's enough to like put this problem to bed at least. So that's our show. Hopefully you found it interesting. I will post the math that I said I would post, and if you have any comments on it or are confused by any of the terms, or I know we like went over a lot of technical stuff. This is probably more technical than most of our shows are. So if anybody was kind of lost or had a hard time following, just drop us a comment on YouTube or on Podbean or on Facebook or wherever with your question. I would be overjoyed to talk more about this topic with you. I don't know if we're going to do another Yak episode or not. We haven't decided yet. Maybe. I don't know. But if you have a suggestion for something you think we'd like to tackle, whether it's religious or not religious or whatever, also drop us a comment on that and we'll almost certainly get to it if you ask.
Yeah. Well, I really appreciate you keeping my eyes glassed over for this one. So
hopefully it wasn't too hard to follow. I tried. This was me trying as hard as I could to be as the least amount technical that I could. Yeah. This was me really trying.
Well,
but anyway, thanks for listening. And remember, you've always got reason to doubt.
Peace out.